What's that? Yeah, that's great. I'm like this, you know. I'm like, something this.
How are you doing? We'll be getting started in just a few minutes.
Hello, I'm Jan Rush. Thank you for coming. Ready.
That's why it's always sensitive. If she gets that,
Yeah. The camera is here. So in order to be on the, kind of have to stand it. And then this, here. That's the there's a tree that's, and then this goes forward and that goes back. Yeah, kind of crazy.
I wish I. And the mic is, it's too beautiful.
Yeah, you can wear this.
Yeah.
Hello, everyone. Welcome. Welcome to the October meeting of the DVAA. I'm Jan Rush. I'm the president. Happy that you're here tonight. Thanks for coming. So we had a great couple of weeks, I think, with all the celestial events that were happening. Remember, Becky Kornikoff went all the way to Iceland to get this great photo of the aurora, and she didn't even need to go that far, did she? But I think she got a pretty good view. Put the lights down, thanks. So we just had a great time the last couple of weeks. I couldn't believe all the photographs were coming in. Here's an example of the, this was from Laura Todd's photo from Hickory Run. And how many people saw the aurora? Okay, great. I think it was just an amazing event. The sun will be pretty active, at least till March, so it's possible we could get some more aurora activity in this area. So keep your ears tuned to the sky weather. And then, of course, we also got a comet. This is comet. Does anyone know how to say this correctly? What is it? Kushanas. Oh, okay, that wasn't the way I was saying it. Yeah, A3, right. And if you haven't seen it yet, there's only a little bit of time. It's getting a little dimmer, so see if you can do it the next couple of days. Here's the finer chart of where to look. It's following a path that's between Venus and Arcturus. Although once Venus sets, maybe you'll be looking between Arcturus and Antares. It's right after sunset is where you want to look, or when you want to look, and start looking as it gets darker and darker. In which case, most of the other stars are not going to be naked eye visible. So you do have to sweep with your eyes, use a binocular sweep to check it out. And for anyone who'd like to see this, grab a copy of this finer chart, there's some back on the table there. So if you haven't seen the comet yet, grab a piece of paper to take with you as you go out. How many have seen the comet? Ah, great. But that's not as many as saw the aurora. So you have some work to do. Okay, what else is happening? Well, the last public star party of our year at Valley Forge will be happening on Saturday, November 9th at 4:30 because sunset is very early. So this is the one you bring the kids and the grandkids to, right? It's not after bedtime. Backup date is Sunday, November 10th. And if you need details, check it out on the website. And these are from last time. There's Al with a little guy at the scope. And here's Kathy at her welcoming table assisted by Xander. Thank you, everybody, for all you did for that party. I understand we had a super great turnout, lots and lots of people. So don't miss the last one of the year. And this is amazing. I don't know. I think I'm right about this. I don't think we missed a single one this year due to weather. I don't know if that's ever happened before. So
The weather gods are listening.
yes, I don't want to jinx it, but okay, other upcoming events. There's an astrophotography workshop tutorial on narrowband processing via Zoom, and that's coming up next week, October 22nd. So this is kind of a special thing that's been scheduled on a specific topic, but it's open to anyone who'd like to join. And the link for joining that is on the website. We have several public events we're trying to get in before it gets too cold. On the 11th, We have a public star party at Fort Washington. November 12th, a public star party at Limerick Township. And then the astrophotography workshop, the regular monthly one, is November 13th. And our next monthly meeting is here in this room on the 15th. And as always, get your details at dva.org. And thanks to Craig for this nice photo of the aurora. Thank you, Craig. All right, there are a few things to mention about regional overnight star parties. This is a really good thing to do to spend some dedicated astronomy time. If any of you who haven't been to an overnight star party, there's one more regional one that you can grab. It's the South Jersey Star Party, which was rescheduled from September. It's now October 24th to 27th. Then there's a winter star party in the Florida Keys, if anyone wants to make that trip. I understand it's a really good time. And also save the date. We've booked the Big and Little Dipper Lodges, April 23rd to 26th for next year's main sequence star party. And that's a good time too. And actually we have 2 lodges, so we've got a good deal of room. There'll be 4 bedrooms plus like 7 dorm style beds, something like that. And kind of unlimited camping, as you see. So lots of room. Okay, our welcoming chair, Brian, couldn't be here, so I'll be announcing the new members this time. This is for September and October. We have Haley Thomas and Suthri Gilroy, and Emma and Daniel Halley, all from Malvern. We have Demain Key and Aslan Yu from Lansdale, Tanmoy Sarker from Devon, Bruce Ruggieri from Westchester, and Greg Venor from Drexel Hill. Any of those people here? Good help. And how many of you are here for the first time? Ah, great. Oh, well, our speaker is here for the first time. That's great. And any of you that want to know more about the club, come see me afterwards, and I'd be happy to meet you if you're here for the first time. And thanks to Stan for this nice photo of the comet. That's what you're looking for, guys. Okay, now we have a an observing talk from Joe Lamb. And I think the topic is going to be solar system, right?
Yes.
Yes.
Solar
Okay.
system.
Sorry for that.
Just a very brief couple minutes.
Would you like the lavalier?
No, the one, the whole.
Yeah, well, no, put one of the other.
Okay.
Sure.
Gotta turn that on, okay? I didn't turn.
Very good.
And remember, you gotta stand for the camera.
Right. Good evening, everybody. I just want to spend a few minutes talking about primarily solar system things. But before I do, I just wanted to show this slide. This is a slide of the blue snowball nebula in Andromeda. And it's a great image, I think. This is a shot of the same thing with the Hubble Space Telescope, and a little bit better. And next to her is the same picture taken by one of our members, Lou Varvaresis. And I asked him a couple months ago if he could, because he was doing some imaging on planetaries, if he would send me one or two of his images. And he sent this picture. And I think it's just amazing. It just kind of blows me away, you know, that somebody could do that. I mean, this nebula is only a couple of an arc minute or so across and very, very small. And he was able to do that. I mean, I think that's just amazing. So shout out to Lou for doing that. That is just, and it didn't require a repair mission. So, I mean, it had a lot going for it. That's right. So, just an amazing shot from someone's backyard with I think it was an 8-inch SCT. Anyway, so I wanted to talk to you a little bit tonight about planets, and it's really a great time for planets. You know, if you come to think of it, you have Saturn transiting at 1022, you have Neptune around 11, Uranus around 2:30, Jupiter around 4:30, and Mars around 6:50. So, you know, if you haven't seen the planets this year, you know, get your telescope out and spend an all-nighter out there, and, you know, you might catch pneumonia, but it'll really be a good thing. So the first two, the first two planets there have passed their opposition points, but we've got the others coming up. And this is a great set of images by Tommy Lasco talking about the tilt of Saturn and its rings. And I just wanted to spend a minute or two on that. As you can see, over the last couple of years, the rings have been closing. The ring angle is becoming smaller and smaller. Tom's image on the 27th probably shows what about probably about a degree and a half, maybe open. And those rings are going to close to nothing in March, and it's going to look something like that. So I just want to say, you know, if you want to see the north part of the rings, that now's your time to do it. Because in March, Saturn will be too close to the sun for observation. And the first time you'll be able to see it really is about the middle of May, when it rises, heliacal rising or rise with the sun. So it'll be observable then. And the other thing I wanted to talk about is the upcoming opposition of Mars. And tonight, Mars is 8.41 arc seconds, so it's really pretty small, on its way to a January 16th opposition, where it will be about 14.5 arc seconds. And this is by no means a great opposition. It's not at near perihelion. And if you look, this January 16th opposition is going to come when Mars is 0.64 astronomical units away. And that's quite a long way from the circled area, which was the 2018 one, when it was 0.38 units. So it's really kind of far. It's not a real great opposition. And you can see the size of Mars, just 14.5. And unfortunately, the next one, which is coming, I think in February 2027, is going to be even worse. It's going to be about 13.5 or 7 arc seconds. So it's getting worse before it's getting better. But the other thing I wanted to mention is the fact that it's going to be really, really high in the sky. So you won't have a lot of atmospheric refraction and seeing issues as well. So it's still, I think, a worthy target for folks that, you know, are planetary observers. And even now in the morning sky, it's way up for dawn. It's really great. Jupiter and Mars are great targets in the morning sky right now. And there's an occultation 3 days before the opposition, where Mars is going to be spotted by the moon the evening of 13th of January. According to Stellarium, the occultation is going to start at 9:19. 13 seconds later, Mars will be half gone. So if you're tired of watching football, it might be a good thing to do on a freezing cold January 9th to get out there and take a look at that. So I just mentioned. And we also have a bright comet in the sky. I guess that's the celestial elephant in the room. I'm going to call it T Atlas because I thought I was pronouncing it wrong. How's it pronounced?
Chinese.
It's Mandarin. Yeah, it's Mandarin Chinese.
Yeah.
And in Chinese, it it means Purple Mountain. And it's because its first discoveries, images were taken at Purple Mountain Observatory in China. And that was January of 2023. And a month later, in February, it was also picked up by the Atlas system in South Africa. And that second system, I don't know much about Purple Mountain, but the second system is really noteworthy. There are 4 telescopes. The program started, I think, in 2015. It's funded by NASA. And there are 4 telescopes. 2 are in Hawaii, one at Mauna Loa and one at Haleakala. A second telescope in Chile, and a third telescope at Sutherland Observatory in South Africa, which is where the image of this was picked up. And it really, the researchers who saw that and figured out the orbit were kind of interested from the very beginning because of the distance from the Earth and the distance from the sun at perihelion, and they kind of figured this was going to be a bright comet. And if I can get this work, there we go. But over the summer, I mean, you saw all the news reports, you know, it was going to break up, it did break up, it was breaking up, it's going to fizzle, it's going to be great. You know, it's still a fairly bright comet. It may not be the comet of the century, but it's still, I think, a worthy object for our observations, especially in the coming year. So, and the numbers on it are just staggering, you know. The perihelion was September 27th, but the period 1.4 billion years inbound. And for a while, they were saying that they were thinking it might be ejected from the solar system. And now I think that the numbers are a little more refined about that. But if you look at the eccentricity, 0.99999, I mean, it's almost a perfect parabola. So I guess that probably had something to do with the uncertainty in the orbit. And the brightness here, I wrote this a couple days ago, was -4. It's actually -4.9. So it really was a pretty bright comet. And this was just a light curve that I got offline about a week or so ago, but it's actually exceeded that in the brightness. And that was my only shot of it. This is taken from Florida about 2 or 3 days after the hurricane. I went down to visit my daughter. And this was when it was -1 on last Saturday night, and not a real bright object, and really, really close to the horizon. It was probably about 2 or 3 degrees above the horizon, and I was able to photograph it. I photographed it from a beach there, and it was, couldn't do much with the image, Paul. That's the orbit. The first orbit is taken from above the plane of the solar system, and the second one is from the plane of the comet. I think you've seen this before, like about 20 times. But this is how the comet's going to look, particularly next week, with the star being tonight. And the one thing I wanted to point out is the moonrise times are going to get better and better and better. And I think that's really, really good because with the higher altitude and the moonless sky, you have much more contrast. We'll be able to image longer, you know, take more sub images and integrate them. And so although the comet has lost brightness and it will continue to do so, I think the next few days and next week or so might be really good. And the other thing is about the tail. You know, the tail they feel is going to be fully developed. It should be fairly long. There should be a separate dust and ion tail. And it should make, you know, for good observing and photography. So I think, you know, let's get out there and try to do it. And this guy, our previous president, Bill McGeaney, is going to be in the hot seat next month at the meeting, like I am right now. And he's going to be reviewing all of our comet images and sketches. So, and I can tell that this was taken, this picture of Bill was taken before the Met series because he has a smile on his face and not now. I mean, I'm a real Sherlock Holmes, you know, but, and Bill is probably down in the dumps. So we got to get his mojo back. And so send him all those pictures and make him happy. And, you know, and let him forget that terrible series with the Mets. So happy hunting, everyone. Thank you so much.
me to extract you.
Thank you so much.
Okay, and now it's time to introduce our program chair, Jeremy Carlo, who will tell us about the upcoming programs and today's program.
All right. Sorry about my voice here, getting over a cold, so I'm doing my Barry White impression. Maybe not quite Peter Steele. Yeah. All right, so I've been looking forward to this presentation for quite a while. I've been trying to get something on the Voyager mission. Kind of special to me because the Voyagers have been around for about as long as I've been alive, actually a little bit longer. I don't remember the Saturn flyby, but I do remember the Uranus and Neptune flybys. The Uranus flyby, you might remember, happened right around the same time as the Challenger explosion, within like plus or minus a couple of days, so it was overshadowed by that. But Neptune was really cool, seeing Sky and Telescope show up at my door and first images from Neptune. But since then, since about 1990, give or take a little bit, Voyager's main mission has been exploring the sun and how it affects the outer solar system. So toward that end, we're happy to have Jamie Rankin, who is the Deputy Director for Science on the Voyager mission, obviously not for the entire time. So, Jamie did her undergraduate work at the University of Utah in physics and music composition, which is an interesting composition or interesting combination. After that, she went to a little place called Caltech to do her PhD, worked with Ed Stone, who's kind of the godfather of the Voyager mission, and also worked on the Parker Solar Probe. Is that correct? And since 2018, she's been an associate research scientist at Princeton University and also the deputy director of the Voyager mission. So please join me in welcoming Jamie Rankin.
Are you on? Where would you like?
I stand or a pocket? Yeah. All right, can everybody hear me okay? Practice this. Okay, great. Thank you very much for the invitation. This is kind of a fun topic to talk about as the sun becoming more active. It's an exciting time on the Voyager mission right now. I'll talk to you some about the latest results, but this is a story kind of some unexpected findings of Voyager's journey through the entire solar system out past the material boundaries of the sun and into the surrounding interstellar medium. And so I'll talk to you about some key observations, not in photons, but rather energetic particles, plasma, magnetic field, materials that cannot even reach Earth. So first, for context, so we are located in this little finger of the Milky Way galaxy called the Orion Spur. Of course, that's not really the real picture. We can't take that picture from our own solar system, but and in between a bunch of dust clouds resides our heliosphere. And so I'll be talking about that. It's our stellar astrosphere, and it has a shape, and we're not sure what the shape is, that we think is somewhat like other astrospheres that we can observe remotely. But our whole history as humankind of studying the stars has been inside out perspective. And now with the Voyagers, we can actually for the first time look kind of back in on our environment. And so we'll start from the inside out perspective. So our star is very large, although size is relative, but 1.3 million Earths can fit inside, and there's a blast wave coming off the sun, a coronal mass ejection, kind of the base of that, and you can see the approximate size of Earth right there. It makes up most matter of the solar system, and the flares put out a lot of energy, many billion times of the power consumption on Earth, and yet it's pretty quiet compared to similar stars. And the sun at its surface is actually only a few thousand Kelvin, but then as it flares out, it gets up to millions of degrees in the corona, 2 million miles from the surface of the sun. a few million miles. Actually, an event to look at, I guess this is not really Voyager, but this is Parker Solar Probe, will make its closest approach on December 24th of this year. Closest flyby of the sun is under 5 solar radii. Now will be a really exciting time to get close into these regions where the winds of the sun kind of lift off. And so there's this charged stream of particles that escape the sun's gravity, and they form this basically supersonic solar wind that flares out in all directions. Here you can see the side view. This is the plane of a kind of center of the sun. Sun's tilted 7 degrees with respect to the plane of the planet, and it puts out kind of wind in all kind of directions. There's a north pole of the sun and a south pole of the sun, and that just has to do with how the inner planetary magnetic field is, whether it's going in the inward sense or the outward sense, and that rotates actually every 11 years. And so this basically flares out, and this time varying solar wind basically expands radially outward, but then the sun's rotating. So a lot of this material, the plasma, magnetic field, they're all kind of tied together. And as they're flowing outward, actually the sun's rotation twists it into this beautiful spiral known as the Parker spiral, which is what Parker Solar Probe was named after, Eugene Parker, who came up with the math to describe the Parker spiral. And these winds, they become supersonic, and then they reach this boundary. They reach a boundary called the termination shock, where they kind of just lose energy. And in that process, basically, it inflates this bubble of gas within the surrounding interstellar materials called our heliosphere. And so this is what Voyager's been studying. Voyager's escaped this actually about 11 years ago. Voyager 1 became the first to basically leave the bubble, and then Voyager 2 joined in 2018, and I'll talk a little more about that. But just to give you a kind of a map of just schematic of what it looks like, there's a supersonic solar wind that flows out about 450 kilometers per second. And at 90 astronomical units or so, that's about where the Voyagers saw the boundary. Basically, that forms a shock. It's like a shock in a plasma sense. And then instead of the sun expanding radially outward, it actually starts to turn back, starts to curve back and become really turbulent in this region right here. And this is called the heliosheath. So it's a slower flowing wind, and it still has all the magnetic fields and all the same plasmas from the sun, but it's just it's a lot more bubbly out there, and it's a lot more turbulent. And then there's this distinctly separate gas of the interstellar material, which is these two gases, they're magnetized plasmas, so they never intermix with each other so far as we've seen. And so we've been looking for the first time on the edge right here about how does the interstellar medium affect our solar material, sun and its material in our heliosphere, and how does our sun actually like affect this surrounding material with the gas? And so that's what I'll be talking about with the perspective of Voyager. But first off, you can make this heliosphere in your own kitchen sink. It turns out, if you turn on your faucet, that is like the sun is the source, and you'll see the water flowing all uniformly outward. Now, the sun, of course, it rotates, so there's an extra little lawn sprinkler effect where it spirals around. But then you'll see that there's like this inner boundary where it becomes really turbulent. And so that's, kind of going in now. So that's actually what the heliosheath is like. It's a slower flow, it just kind of changes, becomes more bubbly. And then eventually it just pressure balances with the surrounding medium and just kind of stops inflating outward. And that is the heliopause. So try it at home. It turns out that the solar cycle produces these it evolves with the magnetic fields of the sun. So there's like a maximum. That's interesting. Maybe they just shorten the cable. So during minimum time periods, there's not very many sunspots. I'm sure many of you, I saw some beautiful pictures of solar observations on your website. We recently had a very weak solar minimum in December 2019. That was one of the weakest solar minima in the space age that we've observed. And then during the solar maxima, which we are now approaching, the sun becomes a lot more active, puts out a lot more material. So it turns out that the Voyagers have been out in the interstellar medium now for a full cycle of this. And so we can actually see how this effect influences that interstellar medium just outside the reaches of the sun's materials. And so it turns out that we actually don't know fully what drives the magnetic fields of the sun. Hopefully in the next decade or so, there'll be images on the poles where a lot of that happens. But we do know that the sun basically is reversing its magnetic field. Its magnetic fields kind of stream out mostly in the equatorial plane during the minima, and they're very well ordered. You can see the field lines going to the poles, and there's a beautiful stream here in the ecliptic. And then it becomes very disordered during the solar maxima time periods. And so I'll be talking a little bit about how this affects the materials that we can see, the galactic cosmic rays. And so thus far, we can observe some galactic materials and some interstellar materials like the dust, like the comets, like that beautiful comet coming from the Oort cloud. But otherwise, historically, we can just see energetic particles coming in from nearby supernova explosions. So those are known as cosmic rays, and they make up every element of the periodic table. People have observed them for over 100 years. And these cosmic ray events sometimes can make air showers in Earth's atmosphere. They can interact with Earth's atmosphere, and there's large observatories that are spread out on the surface of the Earth to measure those interactions. But there's also a lot of space-based detectors. And as the sun is changing in its solar cycle, so larger numbers of sunspots means more activity on the sun, then these particles coming in from other places in the galaxy, they kind of get filtered out. And then when the sun spots are weak and the sun's output is kind of at a minimum, then this radiation from outside reaches kind of maximum levels. And that's related to both kind of the sunspot, which is used to just track the amount of solar activity. And then it's related to also just how this current sheet, basically heliospheric current sheet, rotates. And that's kind of a picture, just like this picture right here. That's sort of how you can imagine that expanding outward into space and kind of rotating over time and maybe even disappearing. We don't know exactly what the processes are as the solar cycle evolves. So it turns out that Voyagers measured all this. 1977 is when they were launched. Voyager 2 in August, Voyager 1 in September. So they just celebrated their 47-year-old birthdays. And the last planetary encounter was Voyager 2 at Neptune in 1989. And then the last image taken was Solar System Family Portrait. And then it's kind of quiet in terms of they turned off the cameras, no more photons being measured. But it turns out that they left on the magnetic field instruments, the energetic particle instruments, and basically nobody knew where was the boundary of our heliosphere. And so the Voyagers just kind of kept going and going. And in 2012, after traveling 1 million miles a day for 35 years, is when Voyager 1 actually reached this boundary of our heliopause and entered into the surrounding interstellar medium. And then in 2018, Voyager 2 joined its twin. So it's only in the last decade that we became interstellar explorers. And here's a picture of those particles, those cosmic rays coming in, galactic cosmic rays. These are the only materials really that we get to see coming in, filtered out by the sun of the interstellar that pass through the interstellar medium. But we do see those effects, just kind of as sunspot number changes and the activity develops on the sun. We see these kind of perturbations here. as those two spacecraft were traveling outward. This is their radial distance up here. The red is Voyager 1, the blue is Voyager 2. This is just the particle intensities on this axis. And both time and distance are kind of on the same axis. But it turns out that in that termination shock region, that inner shock I was showing you, there's not as many variations like this as a function of the solar cycle. It's more just a strong, basically change that reaches this max about right here. And so what they saw how the sun is filtering out all these radiated particles from the surrounding galaxy, and it's actually protecting us from all this radiation. So it turns out this is the first time that we've seen that effect, that the sun filters down 90% of it by the time that all this material reaches Earth. So it's an interesting question about if life could survive actually without this heliosphere filtering out the surrounding radiation. So one of the signatures of reaching interstellar space was that these cosmic rays became very quiet compared to all these disturbances by the sun that affect them. And so the Voyager 1 is currently at 160 astronomical unit, which is about 22 light hour one-way trip. And it crossed the heliopause. So this is, if we consider this plane, the plane of the planets, we're kind of looking at the side view of that. Voyager 1 went up about 35 degrees north, and Voyager 2 went south about 35 degrees south. So they're in kind of very different regions that way. And it measured the density of the plasma out here, the concentration of basically the electrons. And that was found to be kind of this number. People had some rough idea of what that might be. And then the magnetic field strength turned out to be kind of around this number. But it was very interesting when Voyager 2 exited, because we could compare those two results. And so we found, first off, that this distance here, at least from these two shocks of trajectories, straight line trajectories through this outer region of our heliosphere, basically shows us that this heliopause is roughly between 119 and 122 astronomical units. So it's actually fairly consistent where it is. We haven't had any other spacecraft like directly exit. So it's actually a really big question about what's happening with the rest of the shape of our heliosphere. But at least we know in the direction that the whole entire solar system is moving. We know kind of that we call this the nose. We know roughly how far out that boundary is. We also know that the interstellar magnetic field actually comes in at an angle, and it pushes up, it squishes this bottom southward part of our heliosphere. And there's some evidence from remote imaging that it actually pushes it up a little bit and squishes it. It makes it a little asymmetric. But that magnetic field strength is actually much larger down there, seen by a Voyager 2 compared to Voyager 1. And that's also tells us really important clues about how all the material here balances out with all the material out here. And so Voyager, what do the Voyagers measure? Well, they measure there's a long magnetometer boom. So there's a magnetic field instrument at the very, very far end of the boom. There is a large radio plasma wave antenna. And then there's this dish right here is how we communicate back to Earth. And then there's a couple of these cosmic ray measurements. There's two instruments that measure that. On Voyager 2, up until a couple weeks ago, it had the plasma instrument operating on Voyager 2. It failed at Saturn in the early days for Voyager 1. Now, actually, both of those are turned off because of power. But it's basically measuring the perspective from the lens of the particles, magnetic fields, and then the plasma. And so what did it look like when Voyagers entered interstellar space? Well, one of the telltale signs of that was a sudden dropout of materials, of particles that are generated inside our solar system, and a sudden increase of the particles coming in from outside. And so we saw a sudden increase in this red. Those are the galactic cosmic rays of different energies here. And then these other particles here, they're generated within our own heliosphere. And those just kind of bottomed out. People weren't sure exactly what they would expect. Would it be just an empty, vast cosmic emptiness, or would it be full of a lot of materials and particles that are just rarefied? Well, right now we actually call this medium in the very kind of near reaches of the sun, the very local interstellar medium, because the sun actually still disturbs this environment in some surprising ways. So one of the most exciting findings of this mission that were long awaited was to see what the cosmic rays look like when they're not filtered out by our sun's material. So people had no idea what this looked like, and as they were trying to make predictions with models, it was kind of hard to make those predictions without knowing what the source kind of behaves like. And it turns out that these particles could never be measured inside our own heliosphere. They just get filtered out. They don't even make it at these low energies in through there. So it's really neat to see. For example, we could see all elements up to all elements from proton through nickel. But this shows, for example, an exciting thing where the electrons are actually more abundant than the protons out there. And the protons and the helium kind of look about the same in their shape. This is energy here. This is the intensity. But a more interesting part of the findings, and it was seen in this cosmic ray subsystem here, which has these little particle telescopes at all directions. But one of the interesting part is that once the Voyagers crossed that heliopause boundary, there's just no change as a function of distance from the sun. People weren't sure, where does the sun influence on those cosmic rays drop off? And it turns out that the cosmic rays have been just very steady, going further outward as a function of distance. So the question is, are these any more affected by the sun? Well, there's a lot of indications that not so much. So the two Voyagers agree with each other really well in what this spectra looks like. But it turns out that that's not the full story. It turns out that this other instrument, which can step in these octants here and look at different directions, basically it makes has a stepper motor platform here, and it has two telescopes that kind of spin around. The particles can come through in both directions on these telescopes. And they step around, and it turns out that when they looked at a very particular direction with respect to the magnetic field, just perpendicular to the magnetic field, we saw these weird changes here over time. So everything else is pretty quiet. There's a few little jumps up here, but there's a big question: what is doing that? How is that possible? What is happening there? So that was a big surprise here, that there's these time variations. They last like a few years even. They're many months to years, time variations in specific directions. So that was kind of a strange thing. We also found that the magnetic field out there had these strange little bumps and wiggles in it. And so, like I mentioned, first off, the interstellar medium is a very weak magnetic field, slightly stronger in the Voyager 2 direction. But if you look at the average magnetic field of the solar wind, there's a large difference there, and even a larger difference between the magnetic field on Earth at sea level. We found that it was compressed towards that south, but the direction didn't immediately change. So people were puzzled for a while because they were expecting a sudden rotation of the magnetic field to reach the interstellar directions. Now, it wasn't exactly what the Voyagers had seen. But they also found that there's these shocks. They're strange shocks. They're very similar to what the sun produces, even going out to Earth, even that solar storm that interacted with Earth's Earth's magnetosphere to produce the aurora. We see shocks all the time passing through interplanetary space, but these ones were kind of strange. They lasted many weeks to months instead of a couple days. They were very weak, only maybe a 20% change, 50% change, whereas they can be 500% or 1,000% change, factor of 10 in the solar system. They're also very thick. They're 1,000 times thicker than the solar system counterparts. So this is curious, what causes these events? Then we saw these interesting plasma beam effects. So the radio instrument on Voyager 1, because Voyager 1 didn't have its plasma instrument working, it turned out that the radio instrument could pick up these little beams, and that we now know they're beams of electrons that are just generated at the edges of these shocks. And that, when it made this kind of ringing in space, allowed us to measure the plasma. We could measure the plasma density, which was a really important quantity, because when the two spacecraft first reached this strange region, when Voyager 1 actually exited the heliosphere, people had a debate about where were we? Did we really leave? Because the change in the magnetic field was not what they expected. There's not really any change. The cosmic rays changed a lot, and it was these first events right here, first little emissions, that was the tiebreaker to tell us that we were in fact in the very local interstellar medium. And so Voyager 2 also has since seen similar disturbances. Turns out that there's a wideband receiver on Voyager 1. It doesn't quite work on Voyager 2, so they have an electric field measurement that they can still see the disturbances out there. But we still see these events at both spacecraft. And so it actually turns out that these beams of radio waves that get produced are basically particles that just are interacting with these shocks that arrive. They're very weak shocks, but there's still shocks out there. And it turns out that actually energizes particles. So these are the high energy cosmic ray particles, and those little bumps there, that's particles just kind of bouncing off and reflecting off the surface of the shock before the Voyager spacecraft, basically, it overtakes the Voyager spacecraft. In the magnetic field, where these green lines are, that is where those shocks can pass over the spacecraft. And then we also see, after we see these particles energized, we see these beams of radio waves as well. And so it's an interesting picture out there. And Voyager 2 sees similar things. These are these same cosmic rays here. Magnetic field gets disturbed. See these plasma wave events, kind of little singing radio emissions out there in interstellar space. And it turns out that these are caused by outward traveling events that blast off from the sun. So there's a variety of these events, some known as coronal mass ejections, that's where it sends off blast waves. Let's see if it can play the video, maybe. And what we can see is the sun actually will eject the material. Maybe if the video goes, at least just go in here. Oh, interesting. So you see that it's blasts out material, and sometimes other material can blast out, and there you go, with faster material. And it turns out that those blast waves can overtake each other, and they can merge all the way as they're traveling out through the interplanetary medium. And it turns out that and this normally happens when the sun becomes very active near solar maximum, which is where we are right now. And then it turns out that streams from the sun that are still attached to the sun can also whip around and disturb the environment. And so both these are examples of these outward traveling events that can affect all the surrounding medium. And it turns out that when these break off the sun, they can actually, a lot of the slower ones can overtake the faster ones, and they can actually kind of create events that are even seen very far out in our heliosphere. So this is an example of where they saw a particular event back in 2003 near Earth, and they kind of modeled and guessed how various other events could merge with it, and then they had a really good fit. It's the little squiggly line right here, that's Voyager 2, and then the actual data, and they actually predicted when this would arrive at Voyager 2. So it's they understand that pretty well. But what we didn't expect was that how far could these survive? Could they make it all the way out to the edge? And what would they do when they get there? And so actually we had a snapshot of that. This is now those the energetic particles, the ions, cosmic ray ions. This was taken at a time when Voyager 2 was in this heliosheath region right here, and Voyager 1 was out in interstellar space. And we saw the same sort of disturbance that just kind of traveled to the first spacecraft and then went to Voyager 2, and then it actually pushed on the edge here of this heliosphere and sent a wave that disturbed the particles at Voyager 1. And so it turns out that the sun can make these waves that collide with the edge of the heliosphere. And so we can see actually the results in the Voyager 2 data while it was in this region right here. We can see those pressure waves happening from the sun, and it sends these ripples into the surrounding interstellar space. And that is the ripples that we are seeing right here out in the interstellar medium. So these same plasma kind of events that we see, these disturbances out at Voyager 2 in the heliosheath, eventually send these ripples and make shocks out there at Voyager 1. And so here's an example of how a model kind of takes those measurements that's observed at spacecraft near Earth, and it can actually propagate outward all that material and recreate some of the events in the red squiggly right here. That's what the magnetic field of Voyager 1 observations look like. And that is consistent with our picture here. And so actually we used the existence of this event to measure, to make a discovery, because one of the biggest questions out there was, how much pressure is there? Like what is the force that's inflating this whole heliosphere? And does it make sense? And nobody had been able to make an observation of that. People had guesses of what it was, but it turned out that when this event, kind of here in yellow, we call it a global merged interaction region. So that's why it says GMER right there. They just merge. They're very large. They become very large in order to survive out there. And so they just merge, and it's global because it's very large. But it turns out that could be seen by Voyager 1, Voyager 2 in the south, Voyager 1 in the north. So it was a really big event. And it turned out that the speed of that event gave us the total pressure here in this heliosheath. So we're actually able to derive these quantities, which were never known before this event occurred. And it actually made it into Newsweek. And so we got a snapshot of what is actually inflating our heliosphere. And it turns out that that maybe 15% of that is caused by the solar materials that are just blasting out from the sun. But 45% of that is caused by neutral interstellar medium that actually flows into towards our sun, and then the UV from the sun photoionizes it, and then it actually becomes a part of our materials flowing outward. So actually a lot of that pressure is caused by what were neutral atoms in interstellar space, and they come in and become charged and gain energy flowing outward. And then there's some percentage by cosmic rays, and then we don't know what the rest is actually. Maybe it's some people have different theories. Maybe it's electrons, because most of these measurements are with protons. Maybe there's some other effects that we don't know about. So that was a big mystery, which is why it made it into Newsweek back in 2019. But it gave us also a snapshot of all these materials just inside our heliosphere and then outside our heliosphere. And so you can see actually the effects where the magnetic field is very disturbed right here, very turbulent. And then it's like very smooth right here. And there are disturbances, but it's not at all chaotic like this. And then here was kind of strange because even though these events looked very similar to each other, and you can see maybe this little increase right here, that's probably a little spike from a shock that kind of formed right here that got more pronounced in the interstellar medium. But the strange part was this only occurs at one location of the sky. And this occurs at all locations. So we don't quite understand why that is. And so there's exciting mysteries out there still. But then we were more puzzled. We thought that we had to figure it out with all these events traveling out through the interplanetary medium and out colliding with the edge of the heliopause and sending waves into the surrounding interstellar space. And then we were surprised in mid-2020 about this event right here. So these events you can see in the magnetic field, they kind of go up and then they come back down, and then it flattens out, comes up, comes back down, comes up, comes back down. So there's like a pattern here. Well, this one jumped up and then it kept going up. We have no idea why that was. And then it kind of started going down, but it turns out that it's been flat ever since at a totally new level that we didn't expect. And it turns out that those plasma events can actually be used to calculate the density out there, the concentration of the electrons out there. And it turns out that the electron concentration, plasma density, went up too, just at the same time. And it's been flat ever since at a totally new level. So at first we thought, oh, maybe it's just a large event from the sun. Maybe the sun's output just kind of like inflated the entire boundary of the heliosphere. But it turns out that it continues to this day. So 4 years, it's lasted 4 years. We have no idea. This is going up to 2023. Even the latest data shows that it's still happening. It's just still steady at totally different levels than before. And so could this be because of the sun? That's kind of strange that it would last half a solar cycle of a time period. Or is this something about the interstellar medium? And so we are actively looking, this is Voyager 1, at these observations, trying to understand them. And the fun part is the other question that this begs, which is how far out does the sun's influence extend? Because we kind of expected these to get just weaker and weaker and weaker as we're going outward away from the sun. Turns out we have this strong event that just kind of like plateaus. So there's no signs of these events decaying away or anything either. So it's a little interesting. Maybe it's not caused by the sun. Maybe it is. We don't know yet. There are some indications of kind of structure here, and some of these structures are related to the sun. There's a little, you can see imprinted on parts of this. You can see the rotation of the sun. It's 27-day rotational period. You can see that actually in the structure of the small bumps here. And some people have written papers about that. But why is it this new level and what is happening? Well, stay tuned. So here are some of the big questions that we have, which are how far into the interstellar medium can these events travel? How does the sun and its materials influence our surroundings in the interstellar medium? But how does the interstellar medium exert its influence on the sun? It's hard to tell the difference between these, but we do know the sun's a lot more active out there than we had expected. It's an interesting question about without the heliosphere and without it filtrating out the cosmic rays and harmful radiation from explosions of nearby stars, would life exist? What caused this strange new event at Voyager 1? That's a big question. And then there's this question as we're looking back on the heliosphere of understanding more and more about what is the heliosphere's 3D size and shape. So anyway, those are the main questions I was going to end on. And then I'm just going to do a time check because I'm sure somebody will ask what's next, and I have some slides about that too if there's time.
What's next?
Great question. So what is next? Well, it took 35 years for Voyager 1 to reach that location of space, traveling 1 million miles a day. Voyager 2 took even longer. So how can we view this area of the sun and the mixing? Turns out that while the Voyagers were kind of passing through the outer parts of our heliosphere, this other mission, really small mission, launched, and they actually can image all that neutral gas of the interstellar medium coming in. And turns out that most of that medium, most of those gases get modified, the interstellar gas, in a way out here in this heliosheath region, in a way that they can kind of flow in, and then we can measure it at Earth. But it allows us to get a whole sky map of kind of the heliosphere from 3D perspective. And so this mission, basically, there's where Voyager 1 is, there's Voyager 2. This is kind of like a kind of a globe that's kind of, we're looking, if you're to imagine looking at the heliosphere wrapped in a globe, but it's like on your windshield, kind of that's the view from the inside looking outward. This would be the plane of the planets, and this is kind of the direction of travel out of the page. It turns out that they found a structure here, really interesting structure that actually is an imprint of how the magnetic field drapes around the edge of our heliosphere. And so they've been taking these images and trying to basically decipher what is happening with the size and structure of our heliosphere. It turns out that there were recent blast waves from the sun that they saw just basically light up different, they saw the pressure wave basically hit down here first, and then it expanded outward. So that gave them an idea of the scale size of our heliosphere. But it is a hot topic of what exactly is our shape. Some people think it's a croissant shape with 2 little tails. Some people think it's jets instead, a little longer. Some people think it's the shape of a bubble. Some people think it's the shape of a comet. We don't know. It has to do with the balance of the outward flowing gases from the sun, and then the pressures of the interstellar medium. But there is a new mission that's about to launch that will give us much higher resolution kind of images from the inside out of what these boundaries look like. And so those coupled with the Voyager observations will go a long way in telling us about our astrosphere. And that will launch mid to late next year. All right. Well, that's all I have here. Thank you.
Wow, that was fantastic. So are you ready to take some questions?
Ready for some questions?
Okay.
Sure.
I'm gonna ask you that you use the
Okay.
mic for the questions.
Sounds
So,
good.
no, you can use that
Okay,
mic.
okay,
I'll
they
give-
can
yeah,
use that.
so the YouTube folks can hear us. Okay,
Sounds great.
all right.
Can you say something about the health of the spacecraft? I think there was something over the summer about maybe communications weren't working or something. So how are they doing?
Well, that's good question. Well, they're approaching 50 years old in space, and that's a record by a lot. 47 years is a record by a lot. Yeah, there was some recent news about both spacecraft actually. The radiation environment out there that they're experiencing is very intense. So there was a failure on one of the chips on board computer for Voyager 1, and that's why we kind of lost communication for a while. And they figured out how to code around that corrupted piece of memory. Is brilliant. There's a lot of really neat stories in the news on that. People haven't known how long these spacecraft could last. I remember reading in textbooks as a kid that the mission would be done by 2010. And it's kind of like the Energizer Bunny, it keeps going. And so we'll take every moment that we can get. But there is a heroic team at JPL that are dedicated to keeping the spacecraft going, both of them. Some of the challenges are that these are powered, it's tricky to power a spacecraft out there. You can't have solar panels because sunlight's just pretty dim. And so they have these radioactive batteries, and the half-life is 88 years, and we're almost 50 years. So they are, and they're also out in the cold of interstellar space. And so there's some concerns about like what will happen, you know, over time. Will they be able to keep seeing the sun? There's a star sensor and it has to be able to point back. You know, there's all these questions, big unknowns. We don't know, but we are still cheering for the Voyagers to keep going until at least their 50-year birthdays, launch days. And by that time, Voyager 1 will be a full light day away. So that'll be a huge milestone. One way light trip would be a full day, so 2 days to communicate. But I think that'd be a huge milestone. And it's an interesting question of, you know, what will the next thing be out there, and can we travel far deeper into space? What will happen? So people are thinking about that too. What would the next generation spacecraft be to go out there? How fast would it go? Would it go much faster than the Voyagers? So it's an interesting question, and we should start planning now because it'll probably take another couple decades before they reach there. So good question.
I have 2 questions for you. I'll ask the
Okay.
technical one first. I think it was with the Mariner missions. They were discovered to be off course because of asymmetric radiation from the RTGs.
Okay.
Waste heat.
Okay.
Does that affect the Voyager approach?
It doesn't, except maybe I can find a. We do actually see some effects of the RTG in an interesting way as it decays away. Let's see, find the picture in these energetic particles. So let's see, sorry. Way back here. So there is a little bit of a slope there. It's actually more pronounced in some of the other data where we correct for it. But even the trend here going downward, we were puzzled by that. Like, what would that be? And it turns out that the RTG is creating a lot of byproduct materials that these telescopes see over time, and we actually have to correct the data for that decay rate and kind of calculate what fraction over time it will decay and how it will contribute to the signal. And it's a known way, but it's kind of a bit of a surprise. And that change happened more dramatically after we reached the interstellar medium. So that's an interesting thing too. Why didn't we see it the whole time? Maybe it's just because the sun was disturbing things too much. Yeah.
And the non-technical or philosophical question. So given the time of the year that those Voyager probes were launched, I was 5 years old. How does it feel to you to come in from this mission at your age, you know, knowing that it's been going on for longer than you've been around?
Oh yeah, that's a great question. So I think it was Mark Twain who said that we stand on the shoulders of giants, and I know that I do for sure. Ed Stone was my advisor at Caltech. He passed away this year, actually. But there's over a 50-year age difference between us, and it was amazing that he had the patience and the foresight to take on a last graduate student, and I was his last graduate student. And it was incredible to learn from him, learn all that wealth of information. And it's an interesting question. Voyager's been the first in many ways. It's been the longest of new territory in terms of operating a mission, new territory of space, but it's also the first intergenerational mission where it is this case where I was born well after the Voyagers launched, and I think, yeah, they had turned off the cameras basically by the time I was born, and yet here we are making these amazing measurements. And it's an interesting question of how far can we go if people continue to have that mindset of laying the foundations for future generations. And that's a pretty incredible humbling thought. And I hope that towards the end of my career that I can already have set up that next round of Voyagers to go out there. Oh, question.
Missions have taught us a massive, amazing deal of information about the sun and the way that it interacts with things. And I was wondering if the findings from the Voyager missions could teach us more about binary star systems and how they interact with each other, and especially ones where the stars are closer together, how they might impact each other.
Well, that's a really interesting question. So the one thing that has been astrophysically relevant, I think, because it's kind of hard to, there's not really a camera imager working out there right now, but it does turn out that these cosmic rays coming from explosions of like supernova and we don't know actually 100% of where they originate. Some people know that it is maybe related to interactions of stars, but and certainly their explosions. But actually these measurements allow for the first time people to model that. And the fact that we can model how these cosmic rays interact with our own heliosphere, and then we can see like a little shock from the sun kind of change them and energize them, allows people to, in the astronomy community, to actually better constrain their models of how that gets affected by stars. And our own heliosphere is another good example where we know that these neutral materials are a part of what gives the heliosphere its size. And most people, when they're modeling, aren't thinking about the neutral particles because they don't interact with the magnetic fields. They don't really see any of that. It's invisible. But because our sun puts out UV, that actually can change those neutral particles to become ionized. And so it gives people a lot of things to think about, I guess, when they're making these remote observations to consider in their models as well.
I shouted out, do you know what New Horizons?
Maybe I need a little help. Do you know when New Horizons will reach the heliopause?
That's a really good question. So I believe New Horizons is something around like 65 astronomical units, and the Voyagers crossed the termination shock around 80 to 90. Now New Horizons is in the ecliptic plane, whereas the Voyagers were north and south. And so I think they are traveling, so the Voyagers were traveling like 3 astronomical units per year, a little above that. I think the New Horizons are maybe 2 a year or something. So they think maybe in the next decade they could. It depends. The inner boundary from modeling and from those remote observations, we know that termination shock actually breathes and moves in and out a lot with solar cycle. So they could get lucky and it could be coming inward towards them. That's the termination shock. And then the question of the heliopause, it's twice as long as they've been out there right now. So they're around 65, the HUPAS is around 120. So, and I think they launched I think they've been out there for, yeah, 07 or 08, yeah. Yeah, so, so maybe another less than 20 years. Good question.
Of the three closest star, Arcturus, Sirius, and one other one, which one? One is 35 light years away, the others are about 20. Which of those, I think that probably Arcturus would have the greatest effect, if there was any effect. What do you think?
Effect on what?
Us.
Oh, on us. Oh, I see. I see. I see. That's a good question. A very good question. I think there were recent like gamma ray events, gamma ray bursts that we saw. I think at this distance away from other stars, we should be really happy that we're that far away. But I think it matters how active the system is. So I'm not sure if we know for sure like which ones could like be the most hazardous, for example, if there's something some star exploded nearby. It's a good question though. I'm not sure the answer to that.
So thank you for sharing your joy and being part of this multi-generational project. How many other people are joining you in this? How many people are currently being employed to monitor Voyager?
Well, that's a good question. Off the top of my head, I don't know, but I do know that with the flight team, for example, there's been kind of a few phases of people that are flying the spacecraft, and they're continually passing that on to the next generation. With the science, it's an interesting, trickier story because the original people leading the instruments some of them are still leading, but the whole entire community just uses the science. So it's kind of it expands well beyond the immediate Voyager team. There are people being trained. Yeah.
I meant the Voyager team.
Yeah. So specifically the Voyager team, that's a good question. I would guess maybe like 40 or so, maybe on that order. It's not hundreds.
Yeah, but it's 47 years later.
But it's 47 years later, yeah. And there are all sorts of alumni that become very active, especially with these recent anomalies in the spacecraft. I think you could read some of the stories online on how people that worked on the Voyagers during their Saturn encounter, we called them back and said, hey, do you remember how the spacecraft was programmed here? And they turned out to be some of the few people that still know. So exactly. I think there's actually quite a few people on the mission now that maybe first joined over 30 years ago, and then they kind of had their career and then they came back. So it's an interesting thing there. And yeah, we're actively trying to train up the next people as well. But I think more importantly is that we're looking to make sure that all this data, because we don't know how long there's left of this mission, but we want to make sure that all this information with all the people now gets captured really well. So we're pushing a campaign to make sure that we capture people's thoughts and stories and ideas and things for the 50-year anniversary. So and make sure that we have like the papers, the publications that say here's our whole history of observations all the way through to the interstellar space. We want to make sure the data gets preserved. They've done a remarkable job of preserving the data so far anyway. I mean, I think they were, the data was originally coming back on like it's a magnetic tape reel is the memory out there. And the data, the amount of changes in how technology has progressed and how data storage and archiving all this has occurred in the past 35, 40, 40, almost 50 years now. It's like incredible that they kept up with all that. And we're working to make sure that as much of this does get preserved as well, just for future generations.
Because of the great distance that's involved with, I mean, I can't even imagine that, the distance. And because at the time when this was launched, the technology on the end of the Voyager units was not where we could probably do today. I would imagine that they changed the technology on this side to be able to receive the data, because if you can't receive the data from these Voyagers, have they done any studies on that they kind of look out, at least on paper anyway, how far they actually expect the current technology in place to be able to transmit that data back to Earth?
Oh, that's an excellent question. So the transmission is around 30 watts. So that's like communicating with the refrigerator light bulb out there, almost a light day away. That's how Ed Stone described that to me. It's pretty incredible. There is a large kind of array of dishes that communicate with the Voyagers. One thing that is a product of this technology is that the spacecraft are continually transmitting their data, and there's not much onboard storage. There are other missions nowadays, more modern ones, that actually can save all the data, and then they can transmit when it's a good time. But it turns out that that they do have to have these large antenna looking at the Voyagers in order for us to even get the data. It's called the Deep Space Network that is very key to Voyager's success. It consists of there's 3 70-meter dishes and then some 30-meter dishes. And to get back, let's see. I have to find the radio data. They actually have to have 5 station arrays of these dishes to communicate. So it's an interesting question of how far out can we keep communicating. So far, we've still been able to communicate, and especially with Voyager 1. But it's a lot of work on the ground to make that happen, for sure.
It's quite possible that the units that the Voyagers may be working can't receive data from them.
Yeah, there definitely could be a time. We think right now the signal is actually pretty good, and we think that probably there will be other limitations to the spacecraft in terms of like power and other things before it's far enough out that we can't communicate, because the technology on the ground has developed really well. The data processing on the ground has also just developed, and without that being developed over the many decades, it's true, we actually might not still be communicating with them. So it's pretty incredible, and we are hoping that that all that infrastructure continues to be supported and built out and stuff over the future decades, because that will be critical for sending out other missions like this.
So is anyone besides NASA still doing active educational outreach regarding the Voyager mission? Not necessarily at the same level as something like, for instance, the Webb telescope, but are people going out to schools and telling this next generation, hey, we're still operating this amazing project, doing this amazing science?
That is a very good question. Voyager does make the news a lot, and when the recent anomalies occurred on the spacecraft, we got letters from from everywhere, anyone from 5 years old up to 80 years old, like sending letters and wishing the Voyager well for recovery and all that. There's an incredible media amount of just media attention to the Voyager spacecraft. I think a lot of that probably had to do with Ed Stone's work in the planetary encounters. He's very careful to make sure that as the data was coming in, it was shared with the world. And so I think that's why so many people kind of remember those encounters because it was shared with the media the next day after the images came down. And it's amazing that they're still going. And yeah, we're doing our best to continue sharing that with the public. But I'll say that I've been surprised by how much of the public is actually very active in coming to us in some sense, and inviting people to give the talks on the latest updates. And it's a very, very active conversations, I guess, with in terms of doing outreach. Mhm.
Okay, well,
Thank you for an absolutely fantastic presentation. Lots of interest.
just get back when you get your next, when you solve that problem.
There you go.
Yeah.
Thank you very much for the invitation.
Okay, well, thank you very much for your attendance tonight. And go out and find that comment. See you here next month.
Thank
Were you following YouTube?
Thank you.